All right, hello. Welcome to the next video. You're probably watching this with me in class, or well, not watching it with me, but you're probably watching this while you're in class. So I hope you had a nice fall break, and let's go ahead and get into it. So today we're going to be moving forward in Unit 2. Topic 2 is on intramolecular force and potential energy. Okay? So, let me take a drink of my coffee here. All right. This is the learning objective from the AP Chemistry course and exam description for 2.2. We need to be able to represent the relationship between potential energy and the distance between atoms based on factors that influence the interaction strength. Today, for this video, we are mainly going to be looking at this first part of the essential knowledge and this third part. As I'm going to explain here in just a few minutes, we're going to be breaking this video or this topic up into ionic bonding and covalent bonding, okay, because there's a lot to cover. And if I try to do it all in the same video, it's going to be like an hour long, which I know you don't want, and neither do I. So we're going to do ionic bonding first. We're going to be talking once again about Coulomb's law to understand the interactions between cations and anions, positive and negative ions. And we're going to be bringing up the concept of potential energy quite a bit today, okay? And we'll be doing so as well when we talk about covalent bonds in the next video. Okay, your table of contents for this topic, 2.2, like I said, it is going to be two parts, two different videos. For today, part one, we're going to be looking at intra versus intermolecular forces. Those are two different words with two different prefixes. We're going to make sure we know what those mean. Then we're going to talk a bit about ion size and lattice energy, okay? These are in sections 8.4, 8.5 in the textbook. In part two, we'll talk about covalent bonding, and I'll reference this again at that time. There is not going to be a separate problem-solving video for this part one, and that is because I'd rather do it in class on Wednesday, aka tomorrow, mainly because the problem that we're going to be looking at is a real giant pain in the butt. So we're going to do this together on Wednesday in class, okay? All right, so as promised, here's the first little thing we're going to get out of the way. Topic 2.2 is on intramolecular force, okay? Intramolecular forces and intermolecular forces are distinctly different. Intramolecular forces are chemical bonds, okay? They are the forces that hold atoms together into units, okay? Like individual molecules, right, with covalent bonds, or with large-scale crystal structures, which are ionically bonded, okay? That is in contrast with intermolecular forces that occur between molecules, okay? So intramolecular forces make molecules happen. Intermolecular forces are things that can occur between separate molecules, okay? We're going to discuss intermolecular forces at a later date. Today we're just going to be continuing to learn more about chemical bonding, right? So we're really just focusing on intramolecular forces. Usually this is referred to as just bonding, okay, or chemical bonding. Usually this is referred to as intermolecular forces. So more likely than not, if you hear a word like this, it's probably intermolecular forces. A lot of people don't tend to refer to intramolecular forces like this. They tend to say just chemical bonding, okay? All right, so it's all about energy, okay? So if you were with me last year in advanced chemistry, then I'm sure a lot of what I'm going to say here is familiar. I also started to reference some of these concepts before fall break, and so it really is all about energy. So like, why do bonds occur, right? It's all about energy, okay? And specifically, it is about electrostatic potential energy. So those positive and negative charges that we've been talking about, right? Protons and electrons, ions that can have positive and negative charges, the minimization of electrostatic potential energy is what drives atoms to form molecules and crystal structures. Okay, and that is what we're going to be looking at in this topic. We're going to be looking at how do we quantify the amount of energy that's being lowered, or the lowering of the potential energy, and then what are some factors that influence the electrostatic potential energy. Okay, so as I discussed at the beginning, we're first going to be talking about ions. Okay, ionic bonding, right? So we're going to be talking about the size of ions, the distance between ions, and the energy needed to free ions from an ionic solid. Okay, and then we'll get into the covalent bonding stuff in the next video, in which case I'll bring this up again and talk about it a little bit then. Okay, so let's get into ion sizes. Okay, so one thing that you might be asked about on the AP Chemistry exam is the relative size of ions. Okay, so remember that ions are just regular old atoms that have an overall charge, right? Positive or negative. They've either gained or lost electrons. Usually, we will be discussing ions that have adopted the electron configuration of a noble gas. Okay, there were a lot of folks on the previous assessment who struggled with this aspect of ions. So I want to talk a little bit about that right now. So ions tend to form and tend to adopt the electron configuration of a noble gas. Okay, that's that 8 valence electron situation, right? So if I grab my periodic table here, okay, this is what I was talking about when I mentioned all of these elements over here, right, in the first column. Those elements are going to tend to lose 1 valence electron to adopt the noble gas electron configuration. When they lose that 1 electron, they're going to end up with a positive 1 charge, right? And then the flip side is true for elements in this column over here, the halogens. They're going to gain 1 electron to attain that noble gas electron configuration. When they gain their 1 electron, they're going to have a negative 1 charge. I'll probably bring this up again during our actual class time, just to make sure everybody feels comfortable with that. I thought that we sort of had nailed that down in the end of Unit 1, but based on some of the assessment results, that is not true. So we're going to talk about that a little bit more. Okay, so we're going to be talking about ion sizes. Okay, it is also noteworthy to emphasize that we are only really interested in comparing ion sizes. Okay, relative ion sizes, not knowing the absolute value of the size. Okay, so I don't really care what the actual number is. We're more interested in comparing how does this one relate to this one, right? I know how many protons and electrons are here. I know how many protons and electrons are here. Can I predict which one would be smaller, which one would be bigger, based on what we know about those electrostatic forces? Okay, so once again, it's kind of like this is remind you of those periodic trends that we talked about, like ionization energy, electron affinity. We get to think of that a little bit more when we talk about ion sizes. Okay, so here we go. Ion sizes can be thought of as kind of like a periodic trend in a way. There's this picture here which has actual sizes. These are in picometers. Okay, so very, very small. Once again, not really important what the actual number is. What we are doing, right, is we are trying to understand how these sizes sort of relate to one another. And if you were on an assessment, for example, or a homework assignment, given a set of ions, could you predict what the size was going to be? Not the number, but could you predict which one was going to be larger, which one was going to be smaller, that type of thing, okay? So one thing that we can say right off the bat is very, very simple, right? The group trend, right? As you go down the periodic table, clearly the ions are going to get bigger. Just like when we talked about atomic radii or atomic radius, as you go down the periodic table, the atoms get bigger. Okay, and the answer is clear, right? There's an additional energy level full of electrons, right? So the ion is just larger, okay? What is a bit trickier is talking about the period trend. And in fact, it's not even a fair comparison. So let's take two ions that are in the same period. Let's go with sodium and chlorine. Okay, you can see that chlorine is, well, close to double the size of sodium. But let's think about how those two ions were formed. Okay, and you'll see what I mean by it not being a very fair comparison. Sodium, the sodium ion, Na+, lost an electron, right? That's why it's positively charged. But chlorine gained an electron, okay? So that's not really the same thing, right? And so we're not really going to be comparing these two, well, we shouldn't really be comparing these two ions in the same row because they sort of formed in different ways. What we're going to do instead is we are going to compare ions that are isoelectronic, okay? Iso means the same or similar, and electronic is just referring to electrons. So this new vocab word here just means that we're going to be looking at ions that have the same number of electrons, okay? They may have formed in different ways. Some of them may have gained electrons, some of them may have lost electrons, but we're going to be looking at ions that all have the same number of electrons, okay? And remember, ions typically form they typically form in a way that they end up with a noble gas electron configuration, okay? So if we look here at these 5 ions, right? O2, O2 minus, I should say, F minus, sodium plus, magnesium 2 plus, and aluminum 3 plus. Each ion here has 10 electrons, right? Oxygen has 8 to start with, -2 charge. That means it's gained 2 electrons. 8 plus 2 is 10. Same thing here for fluorine, right? 9 plus 1. Sodium, on the other hand, started with 11 electrons, lost an electron, right? Because it has this positive charge. So it's got 10 electrons. And the story is true for magnesium and aluminum as well. Okay? So each of these ions has the electron configuration for the noble gas neon. All right? What I might ask you, or what you might see on the AP exam, or what you are definitely going to see in your homework assignment, is what is the trend in their sizes, right? So like looking at these isoelectronic ions, what's the trend amongst these guys, okay? And so notice, we're not comparing ions that are in the same row, we're comparing isoelectronic ions. So actually it's like the end of this row along with the beginning of the next one. So it's like half of this row, half of that one, all right? So those are the ones that we're going to be comparing with each other. Okay, so in the past, when we've tried to compare like properties, right, of different elements, we've tended to look at really 3 big things, right? Effective nuclear charge, right, the number of protons in the nucleus. Electron-electron repulsions. We looked at that. We drew like those orbital diagrams to like inspect where the electrons were and to see if there was any electron-electron repulsions going on that might be important. And we've also talked about how electrons being, a further distance from the nucleus can impact things as well, right? If they're further out, they don't feel as much of a pull, whereas if they're closer in, they do. So, in the case of isoelectronic ions, these bottom 2 factors actually can't really be the difference, okay? In other words, the only different thing amongst isoelectronic ions is the effective nuclear charge, right? Think about it. All 5 of these ions have 10 electrons, okay? Which means they all have about the same electron-electron repulsions going on, and they all are going to have the same distance from the nucleus situation, right? Like, they have the same electron configuration, right? All 5 of those ions have the same electron configuration. So if we want to talk about how the properties of those ions might be different, we really shouldn't pay attention too much to this business having to do with their electrons. It's more than likely going to be the effective nuclear charge, which determines the size of the ion. And if you take a look here, as we go from O2 O2 minus to F minus to sodium to magnesium to aluminum, right? As we go, increasing in effective nuclear charge, right? 8 protons, 9 protons, 11, 12, 13, the ions get smaller, right? And that makes a lot of sense, right? Because we have the same number of electrons in each situation, but what is happening, right? The number of protons is increasing. That effective nuclear charge is going up. So what's happening is the electrons that are there, right? 10 electrons here, 10 electrons here, 10 electrons here, 10 electrons here, 10 electrons here. They are being pulled closer to the nucleus that has the larger positive charge in it, right? So that is the explanation, okay? And that's not super difficult to understand. The same thing happens with these 5, right? Sulfur, chlorine, potassium, calcium, and gallium, right? As you go across, increasing in nuclear charge, the ions sort of shrink up. And that's because they have the same number of electrons, but the positive charge in the nucleus is increasing each time. Okay? And that really does sort of hold true throughout the periodic table, as long as you're talking about isoelectronic ions, ions that all have the same number of electrons. Okay, so that's ion sizes for you. We're going to also spend some time today talking about lattice energy. Okay, so what is lattice energy? All right, so lattice energy has to deal with ionic bonding. It is defined as the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. And it can be represented by this little equation here. So it's the change in energy that takes place when this happens. Okay, so remember seeing some of those equations like an ionization energy equation or an electron affinity equation. This right here would be the lattice energy equation, okay? So it's the amount of energy, or it's the change in energy, excuse me, that takes place when this process happens. When you take a positively charged gaseous ion, a negatively charged gaseous ion, and they come together to form an ionic solid, okay? The formation of an ionic solid in this way is always exothermic. Okay, energy is released from the system. Okay, it is energetically favorable. All right, and I can explain that through taking a look at this graph here. Okay, let's make sure we understand what the axes of this graph is, or what the axes are. So the x-axis of this graph is labeled r. R is the radius or distance between the two ions in this case. Okay. So if r is very large, that's over here on this end of the graph. If r is very small, aka 0, then it would be right here, right, at the origin of the graph. The y-axis is potential energy, okay? And once again, I don't want us to get hung up on the positive and negative signs here, but think of it as, well, okay, so if I go back a number of slides here, I said it was all about energy, right? And something that I'm not sure if I read exactly is this first sentence here. In natural processes, there is a tendency toward lower energy. Okay, lower energy in this case means lower potential energy. Okay, so the more negative the potential energy gets, that's what nature tends to do. Okay, is to minimize energy, or to minimize potential energy in this case. Okay, so let's try to cross that hurdle here. Let's actually look what this graph is showing us. Okay, what this graph is showing us is that there is a bit of a sweet spot. Okay, when two oppositely charged ions are, say, in the gaseous state, separated from each other, right? R is very big. The potential energy is roughly 0. Okay, so it means that there's really no interaction between those two ions. They're like separate. Okay, there's no interaction. They're too far apart to feel each other's attraction or repulsion, and so there's no real potential energy to even talk about. However, when you bring those ions closer to each other, okay, just like if you were to bring two magnets closer to each other, they start to feel the attractive forces that bring them together. Okay, and then imagine this, right? Imagine you take your two oppositely charged ions, you're holding on to them, you get them close to each other, and you let go. Okay, what they are naturally going to do is move towards each other, right? Now, the question is, right, how close do they get, right? Because if you look here on the other side of this graph, if they get too close, right, if the distance between them gets too close, well, we end up in a very like high energy situation. So what's all that about? So there is a sweet spot, okay? So I'm going to try to explain this one more time here. The attractive forces bring the ions together, okay? They will naturally come together into this sort of stable state, this low energy, low potential energy situation. If they get too close, however, you've got to consider what these ions are actually made of, okay? They're oppositely charged, right? This one might be positive, this one might be negative, but those ions are made of a nucleus and electrons, right? So each ion has a positively charged nucleus and negatively charged electrons around it. So if they get too close, right, then the nuclei in each ion start experiencing a repulsion effect away from each other, okay? Same thing with sort of the electrons that make up the core electrons of those ions, right? Those negatively charged electrons on the outside of the ion, if those get jammed too close to each other, they will also experience some repulsive forces that try to keep them apart. So there is a sweet spot, right? The two oppositely charged objects will come together, but they won't merge into the same thing necessarily because of the nuclei and the electrons that actually make up those ions. Okay, so it's a balancing act between the attractive forces and the repulsive forces. Okay, and so there is a sweet spot. Okay, this coincidentally, right, does actually end up being a number. Okay, so there is a number that you can like determine for different pairs of ions. That is sort of the bond length. Okay, it's the distance, right, between the nuclei of those two ions, right? So that's something interesting that we're going to be looking at here in just a few minutes. Okay, but then you can also sort of figure out what that potential energy is. This right here is essentially what the lattice energy is. It is the amount of energy that you lower. That's a bad way of putting it. It's the amount of energy that is released from the system by bringing the two ions together that were once separate, right? If I read this lattice energy definition again, lattice energy is defined as the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid, right? So it's like the energy change from this situation where they are separate to this situation where they are together, okay? And so it's always an energetically favorable thing, okay, an exothermic situation whenever two oppositely charged ions come together from being, infinitely far apart. Okay. I wanted to show you this. This is not something that I think is particularly important for the AP exam necessarily, but I love talking about crystal structures. It's very cool. So I'll just spend a minute or two on this. Ionic solids, when you bring ions together and they form solids, they exist in the form of crystal structures, okay? So this is just an example of what sodium chloride might look like, for example, salt, table salt. The chloride ion would be the larger one, the sodium would be the smaller one. Here's another look at what this kind of looks like. Notice how, so let's say we're looking at this this chloride ion here in the middle, the green one, okay, that'd be negatively charged. Notice how the six closest things to this green ion are all positively charged sodiums, right? Look at this. If I go out here, that's a positively charged sodium. If I come out here, that's a positively charged sodium. Over here, positively charged sodium. Here, positively charged sodium. And then up and down, positively charged sodiums. Okay, so like this guy, this green guy, the chloride, negatively charged chloride, has 6 neighboring sodium ions that it is closest to. Okay, and if this were to be replaced by a sodium, then it would be surrounded by 6 chloride ions. This is a repetitive structure called a crystal structure that minimizes the distance to oppositely charged ions, but maximizes the distance to similarly charged ions, while still being in solid form. Okay, and so this right here is called a crystal structure. This is called the sodium chloride structure. It's this like 1-to-1 ratio, okay, of like sodium to chloride. The sodium chloride structure happens in other ionic compounds as well, as long as things are like 1-to-1 ratio. There can be other crystal structures that form or that can be adopted based on a variety of different factors. So it can be like the number of different ions, whether or not there's like a polyatomic ion involved, for example, the size of the ions. If the size of the ions is very different, then sometimes this crystal structure will not be the most energetically favorable. And then also the ratio of ions. This is a 1-to-1 ratio, so this is kind of nice and easy to imagine. But let's say you had like a 1-to-4 ratio, right? Or even a 1-to-6 ratio or something crazy like that, right? Then this wouldn't really work, right? Because you couldn't make something that looked nice and simple like this. So the crystal structures get a bit more complex, but it is still sort of an infinitely repeating pattern that does sort of minimize the energy involved. Okay. Once again, crystal structures I don't really think are something that are explicitly assessed on the AP exam. I took a class in college called materials science, materials engineering courses, where we learned about crystal structures in ionic compounds, in metals, in lots of different sort of things like ceramics. And so it's interesting things to learn about. Maybe not right now, but later on in your science career. Okay, so let's get back to talking about lattice energy. And what we're going to do is we're going to look at how the size of an ion and the charge of the ions might impact that lattice energy term. Okay, so just remember, right? Lattice energy is the amount of it's the change in energy that takes place when these ions are brought together, right? And remember, there's that sweet spot. Okay, so what we're going to look at is this equation here, which looks very familiar, right? This is a form of Coulomb's law. We're going to look at how these factors, the ion size and the ion charge or the ionic charge, might impact the lattice energy of a crystal structure. Okay? All right, so let's look at how ion size might impact lattice energy. Okay? So if you have large ions, then the distance between the ions in the ionic solid is going to be large. If the ions are small, then the distance between the ions is going to be small, right? So like look at this picture here of this crystal structure, right? If this green and purple thing, if those are very big, then the distance between the nuclei is going to be bigger than if you had small ions, right? If you had smaller ions, then the distance between the two nuclei is going to be smaller, okay? That's kind of simple, right? What that means, okay, is that in the large situation, right, if the radius or the distance between the two ions is increasing, right, so if the denominator here is increasing, then the lattice energy, that's this E term here, energy, then the lattice energy is actually going to go down, right? If the, and that's just based off the math equation, okay, but let's think of it in sort of, our imagination terms, okay? If the ions can't get as close together, then the energy doesn't get as minimized, right? I mean, if I go back here, right, I know that we were talking about those repulsive forces. Don't consider that for just a second. Think about if these two ions, these two spheres, think about if they were larger, right? They literally couldn't get as close, right, because they're just larger, right? The ions are bigger in size. And so you would have to sort of stop a little bit further out here. That's not a perfect way of putting it, but that does kind of get the point across, okay? So once again, if the distance between the ions is larger, then the lattice energy is not going to be as large, and so that just means that it's less exothermic or less favorable. On the flip side, if the radius between the distance between the two ions is smaller or decreases, then the lattice energy is going to be bigger or more exothermic, more favorable. okay? And there's actually a example that I can give you. Okay, and I have the values here written down. Oops, I have the values written here on a piece of paper. I didn't want to spoil it for you. So let's look at this example here. Lithium fluoride versus sodium chloride. Okay, both of these ionic compounds have charges of +1 and -1. Okay, so like lithium is +1, fluorine is -1, sodium is +1, chlorine is -1. So the charges are the same. However, sodium and chlorine are in the third row on the periodic table, whereas lithium and fluorine are in the first or are in the second row. Okay, and you can actually go back and look at the sizes here. Here's sodium and chlorine. Here's lithium and fluorine. Right? Sodium is bigger than lithium. Chlorine is bigger than fluorine. Okay? So those are the two situations. Small ions versus big ions. Okay? Which would have the larger or more exothermic or more favorable lattice energy? The smaller ions or the larger ions? Well, I just told you, right, that if the distance between the ions is smaller or decreases, then the lattice energy is going to increase, right? And that makes sense in terms of the math here, right? If this number gets smaller, then we're dividing by a smaller and smaller number, and so our energy is actually going to be bigger. Well, here's the numbers, okay? Lithium fluoride has a lattice energy of about 1,023 kilojoules per mole. Sodium chloride's is smaller at about 786 kilojoules per mole, okay? Not a huge difference, but it is a difference, okay? And it can be predicted by thinking about the sizes of the ions, okay? It's important to note, though, that I've controlled for the other variable, right? The charges themselves are the same, +1, -1, +1, -1, all right? That is another thing you have to keep in mind, okay? So you have to keep in mind the charges as well, okay? And I think this is the last slide. Yeah, this is the last slide, so we're getting close to the end of the video. Okay, so you can talk about the distance. You can also talk about the magnitude of the charge, okay? The ionic charge on the different ions. If the ions that are involved have large or larger ionic charges, the amount of attraction between the ions is larger, okay? To put that simply, right, if you've got a +1 and a -1, those are going to feel a certain amount of attraction. If you have a +2 and a -2, those are going to be more attracted to each other than the +1 and the -1. That makes sense, right? The magnitude of the charge is larger. They feel more attraction towards each other, okay? So let's look at that in terms of the math, okay? If Q1 and Q2, right, those are the two charges, if those both increase or are bigger, then your energy or your lattice energy is going to be more exothermic. It's going to be bigger, it's going to be more exothermic, it's going to be more favorable. However, if your Q1 and Q2 are smaller, or if they decrease, then the lattice energy is also going to decrease, right? They're going to be less exothermic, less favorable. I have another example for you. Okay, so let's look at two ionic compounds. This time I've picked elements that are in the same row. Okay, so the ion size is about the same in each situation. Sodium is roughly the same size as magnesium. Chlorine is roughly the same size as sodium in terms of the ions. What's different, though, is the charge on the different ions. Okay, sodium is +1, chlorine is -1, magnesium is +2, and sulfide or sulfur is -2. So which one is going to have a larger, more exothermic, more favorable lattice energy? Okay, well, Q1 and Q2 are both bigger in the magnesium sulfide situation, so we would expect, right, if the charges are bigger, there's a more attraction, so the lattice energy is going to increase. It's more exothermic and more favorable. Is that true? Well, let's look at the numbers here. Okay, so for sodium chloride, that's the +1 -1 situation. That's 786 kilojoules per mole. For magnesium sulfide, which is +2 -2, it's 3,406. Okay, so once again, those numbers are 786 for sodium chloride, 3,406 for magnesium sulfide. Huge increase. Okay, so the increase on the previous slide with the distance difference was only about 250. Okay, this difference is more like, I don't know, 2,700. okay? Something like that, 2600. So why the big difference? Why the huge difference? Well, it can be explained by looking at this formula, okay? Q1 and Q2 get multiplied by each other, okay, the magnitude of the charges. What's plus 1 times minus 1? Well, it's just minus 1, right? Like, if you think of the absolute value, right, 1 times 1 is 1. What is 2 times 2, right? 2 times 2 is 4, right? So when you have a ionic compound here that's got plus 2 minus 2 and you compare it to one that's only got plus 1 minus 1, the lattice energy is actually going to be like 4 times larger than it would be in this situation, right? Because we're multiplying these charges times each other, okay? And so if you look at the numbers, actually, it's about 800 compared to 3400. That's roughly 4 times as big. I think it's more like 4.5 or something like that. You know, because there's other factors that can come into play, like the sizes and things like that. So your homework assignment is going to involve you looking at the size of ions, and it's going to involve you looking at lattice energies and predicting based on ion sizes, ionic charges, number of ions, which lattice energies might be larger, which ones might be smaller, right? By trying to compare the properties of the ions that are involved, okay? And then, like I said, we are going to look at the problem-solving portion of this topic. We're going to look at in class on Wednesday. Okay, I'll talk a little bit about that when I see you guys in class, okay? All right, thanks a lot for watching, and I'll see you in the next one.